Welcome to the Science Lullaby. I'm glad you're here. Maybe you're lying in bed after a long day, your room softly lit or completely dark, your body finally beginning to relax. Or maybe you're simply curious, letting your mind wander while you rest. However you've arrived, this space was created for moments like this, quiet moments where learning doesn't rush you and curiosity feels calm instead of demanding. Tonight, we're exploring one of the deepest questions science has ever asked. A question that seems simple at first, but becomes more mysterious the longer we sit with it. What is reality, really? Every day, we move through a world that feels solid and reliable. We see objects, hear sounds, feel time passing, and assume that what we experience is the world as it truly is. But modern science tells us something surprising. What we experience as reality is not a direct copy of the outside world. It is something carefully constructed by the brain, moment by moment, using limited information from our senses. Physics, neuroscience, and psychology all suggest that reality is not as straightforward as it seems. Light, sound, color, space, even time itself may not exist in the way we intuitively imagine. At the smallest scales of the universe, particles behave in ways that defy common sense. At the level of the brain, perception turns raw signals into a coherent world that feels seamless and complete. In this video, we'll gently explore how science understands reality, not as something fixed and absolute, but as a dynamic process shaped by observation, perception, and consciousness. We'll look at how the brain builds an internal model of the world, how physics challenges our ideas about space and time, and why different observers may never experience the same reality in exactly the same way. There's nothing you need to memorize here, and no need to stay fully alert. This is a slow journey. You can listen actively or simply let the ideas pass through your mind as you relax. If you fall asleep along the way, that's perfectly fine. The information doesn't need your effort to be meaningful. As we move forward, we'll begin by clarifying what scientists actually mean when they use the word reality. Because before we can question whether reality is subjective, simulated, or shaped by consciousness, we first need to understand how science defines the world we think we know. Now, let your breathing slow. Allow your thoughts to soften and settle into a comfortable position. In the next part, we'll begin by asking a simple but powerful question. What do we really mean when we talk about reality at all? When scientists talk about reality, they usually mean something very specific. They are not talking about personal feelings, beliefs, or interpretations. They are referring to the physical world that exists independently of any single observer, the structures, forces, and laws that continue to operate whether or not anyone is watching. At least this is how reality has traditionally been defined in science. In classical physics, reality is made of objects with clear properties. A table has a position, a mass, and a shape. A planet follows a predictable path through through space. Time flows forward at the same rate for everyone. In this view, reality is stable, objective, and measurable. If two people observe the same event, they should agree on what happened, because the event exists independently of them. This definition worked well for centuries. It allowed scientists to describe motion, gravity, electricity, and mechanics with remarkable accuracy. But as science moved deeper into the nature of matter and energy, cracks began to appear in this simple picture. At very small scales, reality stopped behaving like a collection of solid objects. Instead, it began to look more like a set of probabilities, relationships, and interactions. In modern physics, reality is often described in terms of fields rather than objects. Particles are no longer seen as tiny solid dots. They are excitations in underlying fields that stretch across space. These particles do not always have definite positions or energies until they are measured. Before observation, they exist as a range of possibilities rather than a single outcome. This creates an important shift in how reality is defined. Instead of being a fixed stage where events unfold, reality becomes something that depends on interactions. Measurement, observation, and context start to matter. What exists is not just what is out there, but also how systems interact with one another. Neuroscience adds another layer to this picture. From the brain's perspective, reality is never accessed directly. The brain does not see light, hear sound, or touch objects. It receives electrical signals from the eyes, ears, and skin, then uses those signals to build a model of the world. What you experience as reality is already a constructed interpretation by the time it reaches your awareness. This means that even if there is an objective physical world, your experience of it is always filtered. Colors are interpretations of wavelengths. Sounds are interpretations of air vibrations. Even the feeling of time passing is something the brain actively generates. Reality, as you experience it, is a collaboration between the external world and your nervous system. Because of this, scientists often separate reality into two layers. There is the underlying physical reality described by equations and measurements, and there is perceived reality, the version of the world created by the brain. These two layers are deeply connected, but they are not the same thing. Understanding this difference is essential for exploring deeper questions about consciousness and perception. As we move forward, this distinction will become increasingly important. To understand whether reality is subjective, simulated, or observer-dependent, we first need to understand how perception works. In the next part, we'll explore how the brain transforms raw sensory information into the rich, continuous world you experience every moment. Now, let your attention rest lightly and allow these ideas to settle. In the next section, we'll look more closely at the difference between reality itself and the way the mind perceives it. The difference between reality and perception becomes clearer when we look at how the brain actually works. Your brain is not a passive receiver of the world. It is an active system that constantly predicts, interprets, and fills in missing information. What you experience as the present moment is not a direct feed from the outside world, but a carefully constructed internal model. Every second, your senses collect incomplete and sometimes ambiguous data. Light hits the retina, sound waves reach the inner ear, pressure activates receptors in the skin. But these signals are noisy and limited. The brain's task is to take this imperfect input and turn it into something stable and meaningful. To do this, it relies heavily on past experience, expectations, and probability. This is why perception is not the same for everyone. Two people can look at the same scene and notice different details. They may even disagree about what they saw. The brain prioritizes information that seems most relevant for survival and understanding, not necessarily what is most accurate in an absolute sense. Reality, as experienced, is optimized for usefulness, not truth. Visual illusions provide a clear example of this process. In many illusions, the brain confidently perceives motion, color, or depth where none exists. These illusions are not errors in the eyes. They are the result of the brain applying rules that usually work well in the natural world. When those rules are applied in unusual situations, perception diverges from physical reality. Even basic properties like color do not exist independently in the world. Objects do not contain color. They reflect certain wavelengths of light. Color is the brain's interpretation of those wavelengths, shaped by lighting conditions and context. The same object can appear completely different under different conditions, even though nothing about the object itself has changed. Time perception works in a similar way. The brain does not measure time like a clock. Instead, it reconstructs time from sequences of events, changes, and memory. When you are relaxed, time may seem to slow down. When you are stressed or focused, it can feel as if time speeds up. The external flow of time may be constant, but your experience of it is flexible. This shows that perception is an active process, not a mirror of reality. The brain continuously updates its internal model based on new information, correcting errors when predictions fail. Most of the time, this process is so smooth that we never notice it. Reality feels immediate and obvious, even though it is the result of complex computation. Understanding this distinction helps explain why reality can feel so solid while being deeply constructed. It also opens the door to more challenging questions. If perception shapes our experience so profoundly, then how much of what we call reality is created by the mind itself? In the next part, we'll explore this idea further by looking at how the brain builds a predictive model of the world and why some scientists describe perception as a kind of internal simulation. Now, let your breathing remain slow and steady as we move forward. One of the most influential ideas in modern neuroscience is that the brain does not simply react to the world, but actively predicts it. According to this view, often called predictive processing, the brain is constantly generating expectations about what it is about to perceive. Sensory input is then used not to build reality from scratch, but to correct these predictions when they are wrong. In this framework, your experience of the world is largely driven from the inside out. The brain builds a model of reality based on prior knowledge, memory, and learned patterns. Incoming sensory signals are compared against this model. When the signals match the prediction, perception feels smooth and effortless. When they don't, the brain updates its model to reduce the error. This helps explain why perception feels so stable despite the fact that sensory input is incomplete and constantly changing. Your eyes, for example, take in only a small portion of the visual field with high detail. Yet you experience a continuous, detailed world. The brain fills in the gaps using prediction, creating the illusion of completeness. This predictive model is not limited to vision. It applies to sound, touch, movement, and even your sense of self. The feeling that you inhabit a body, that your thoughts belong to you, and that the world is happening out there are all part of a model the brain maintains. These experiences feel immediate and real because the brain's predictions are usually accurate enough to keep the system stable. When prediction breaks down, perception can change dramatically. In altered states of consciousness, such as dreaming, meditation, or certain neurological conditions, the balance between prediction and sensory input shifts. During dreams, external sensory input is largely disconnected, so the brain's internal model runs almost entirely on its own. This is why dreams can feel vivid and immersive, even though they are generated internally. Some neuroscientists describe waking reality as a controlled hallucination. This does not mean that the world is imaginary, but that perception is a guided construction. The brain hallucinates a world based on its best guesses, then adjusts those guesses using sensory evidence. Most of the time, this process works so well that the distinction between prediction and perception disappears. This idea has important implications for how we think about reality. If the brain is constantly simulating the world, then what you experience is always one possible version of reality, shaped by biology and history. Reality becomes something you participate in, not something you passively observe. As we continue, this raises a deeper question. If perception is a simulation built by the brain, what happens when we examine the physical world itself? Does reality remain solid and well-defined at its most fundamental level, or does it also become uncertain and probabilistic? In the next part, we'll turn to physics and explore how light, sound, and matter challenge our everyday intuitions about what reality is made of. When we look more closely at the physical signals that create our experience of reality, it becomes clear how indirect our connection to the world truly is. Light, sound, and touch feel immediate, but each of them is the result of complex translation processes that occur entirely within the nervous system. What you experience is not the physical signal itself, but the brain's interpretation of it. Light is a good example. In the external world, light is electromagnetic radiation moving through space at different wavelengths. These wavelengths have no color on their own. When light enters the eye, it stimulates specialized cells in the retina. The signals from these cells are sent to the brain, where they are combined, compared, and transformed into the experience of color. Blue, red, and green are not properties of objects. They are experiences created by neural processing. Sound works in a similar way. In the air, sound is nothing more than pressure waves. These waves vibrate the structures of the inner ear, which convert mechanical motion into electrical signals. The brain then organizes these signals into pitch, volume, and rhythm. Music, voices, and ambient noise all emerge from this interpretation. Without a brain to decode them, these vibrations would never become sound as you know it. Touch, temperature, and pain are also constructed experiences. Nerve endings in the skin respond to pressure, heat, or chemical changes. The brain combines these signals with context and memory to create sensations. This is why the same physical stimulus can feel pleasant in one situation and uncomfortable in another. The experience is shaped not only by the signal, but by the brain's expectations. These translation processes reveal an important truth. Your senses do not give you access to reality as it is. They give you access to a useful representation of reality. Evolution shaped perception to support survival, not to provide a perfectly accurate picture of the world. The brain prioritizes what is relevant, predictable, and meaningful. This idea challenges the assumption that we experience the world directly. Instead, we live inside a sensory interface, similar to a dashboard. Just as a car's speedometer does not show you the motion of every engine component, perception does not show you the full complexity of physical reality. It shows you a simplified, actionable version. Once we accept this, the question of reality becomes more subtle. If the physical signals themselves are invisible to experience, and everything we perceive is a translation, then reality exists at multiple levels. There is the underlying physical process, and there is the experienced world created by the brain. As we move forward, this distinction will lead us into even stranger territory. When we examine matter and space at the smallest scales, the physical world itself begins to behave in ways that defy common sense. In the next part, we'll explore how modern physics challenges the idea of solid, stable matter and introduces uncertainty at the foundation of reality. Now, allow these ideas to settle as you continue to relax. Time feels like one of the most stable features of reality. It seems to move forward at a steady pace, carrying moments from the future into the present and then into memory. We organize our lives around this flow. But when scientists examine time closely, especially through the lens of physics and neuroscience, its apparent solidity begins to dissolve. In everyday experience, time feels universal. We assume that a second is the same for everyone, everywhere. Classical physics supported this idea, treating time as an absolute background against which events unfold. But modern physics tells a different story. According to Einstein's theory of relativity, time does not flow at the same rate for all observers. It depends on speed and gravity. Clocks moving at high velocities tick more slowly. Clocks in stronger gravitational fields run at different rates than those farther away. This means that time is not a single shared river. It is woven into space itself, forming what physicists call space-time. Different observers carry their own versions of time, shaped by their motion and position in the universe. There is no universal now that applies everywhere. What feels like the present moment to you may not exist in the same way for someone moving differently through space. Neuroscience adds another layer to this picture. The brain does not perceive time directly. Instead, it reconstructs time from changes, rhythms, and memory. Your sense of duration depends on attention, emotion, and expectation. When you are calm, time can feel expansive. When you are anxious or focused, it can seem compressed. The brain stitches moments together into a continuous experience, even though neural processing happens in discrete bursts. Memory plays a central role in this construction. Without memory, there would be no sense of past. Without anticipation, there would be no sense of future. The present moment, as you experience it, is already slightly delayed, assembled from sensory information that arrived fractions of a second earlier. What feels like now is actually a carefully synchronized illusion. This raises a profound question. If time depends on both physical conditions and neural processing, then what does it mean to say that time is real? Is time a fundamental feature of the universe, or is it a useful framework that emerges from deeper processes? Some theories of physics suggest that time may not exist at the most fundamental level at all, but emerges from relationships between events. When we consider time this way, reality becomes less like a flowing river and more like a vast structure where moments are connected but not necessarily moving. Our experience of motion through time may be the brain's way of navigating this structure, just as perception helps us navigate space. As these ideas settle, we are led toward an even deeper challenge to our intuitions. If time and perception are not fixed, what about matter itself? Is the physical world truly solid and continuous, or does it also dissolve under close inspection? In the next part, we'll turn our attention to matter and space, and explore how modern physics reshapes our understanding of what reality is made of. At first glance, matter feels solid and dependable. Objects have weight, shape, and resistance. You can touch a surface and feel that it exists. For most of human history, this sense of solidity defined reality itself. Matter was assumed to be made of tiny, hard pieces that fit together like building blocks. But as physics looked deeper, this picture began to change. At the atomic level, matter is mostly empty space. Atoms consist of a small, dense nucleus surrounded by electrons that occupy regions of probability rather than fixed paths. These electrons are not little particles orbiting like planets. They behave more like waves, spread out across space, only taking on definite positions when measured. What feels solid is actually the result of electromagnetic forces preventing atoms from passing through one another. When we go deeper still, the idea of solid particles becomes even less clear. In quantum physics, particles are described by wave functions, mathematical expressions that represent possibilities rather than certainties. Until an interaction occurs, a particle does not have a single definite state. It exists as a range of potential outcomes. Measurement does not simply reveal reality, it helps define it. Space itself also turns out to be far from empty. According to quantum field theory, every region of space is filled with fluctuating fields. Even in a perfect vacuum, particles briefly appear and disappear, borrowing energy from the vacuum itself. What we call empty space is an active, dynamic environment, constantly changing at microscopic scales. This challenges the idea that reality is built from stable components. Instead, reality looks more like a network of relationships and interactions. Matter is not a collection of objects sitting in space. It is a set of processes unfolding within fields that extend throughout the universe. Stability emerges from balance, not from permanence. These discoveries force us to reconsider what it means for something to exist. If particles do not have definite properties until they interact, then existence itself becomes contextual. Reality depends on interactions, measurements, and relationships, rather than isolated things. For everyday life, this strange behavior is hidden. The quantum world averages out, producing the stable reality we experience. But at its foundation, reality is probabilistic and fluid. The solid world you move through is an emergent phenomenon, arising from deeper rules that operate beyond direct perception. This brings us to a crucial turning point. If matter and space are not fixed, and if their properties depend on observation and interaction, then the role of the observer becomes impossible to ignore. The next step is to examine how observation itself influences reality at the most fundamental level. In the next part, we'll explore how quantum physics introduced the idea that the observer may play an active role in shaping what becomes real. When quantum physics began to take shape in the early 20th century, it introduced one of the most unsettling ideas in all of science. At the smallest scales of reality, the act of observation appears to matter. Particles do not behave as fully defined objects independent of measurement. Instead, their behavior depends on how and whether they are observed. In many quantum experiments, particles exist in a state called superposition. This means they do not occupy a single position, energy, or state, but multiple possibilities at once. These possibilities are described mathematically by a wave function. As long as the system is left unmeasured, the wave function evolves smoothly, representing many potential outcomes simultaneously. When a measurement occurs, something changes. The range of possibilities collapses into a single outcome. A particle is found in one position, with one value, at one moment. This transition from possibility to actuality is known as wave function collapse. What makes this process strange is that physics cannot clearly explain why or how collapse happens. The equations describe probabilities, but the act of observation seems to select a specific reality. This raises a difficult question. What counts as an observation? Is it a conscious observer, a measuring device, or any physical interaction? Different interpretations of quantum mechanics answer this differently. Some suggest that any interaction with the environment is enough. Others argue that measurement is a more fundamental process that cannot be fully reduced to physical contact alone. Regardless of interpretation, the implication is profound. Reality at the quantum level does not appear to be fully determined until an interaction occurs. Before that, what exists is not a single outcome, but a structured set of possibilities. Reality becomes something that crystallizes out of uncertainty. This does not mean that human minds create reality at will. The outcomes of measurements follow strict statistical rules, but it does mean that reality is not simply waiting, fully formed, to be discovered. It is revealed through interaction and, in some sense, participation. For many physicists, this was a turning point. The classical idea of a detached observer watching a fixed universe no longer applied. The observer became part of the system being studied. The boundary between subject and object began to blur. As these ideas developed, scientists searched for ways to make sense of this strange relationship between observation and reality. Some interpretations attempted to remove the observer from the equation entirely, while others embraced the idea that reality branches into multiple outcomes. In the next part, we'll explore one of the most famous responses to this problem: the idea that every possible outcome actually happens, each in its own version of reality. One way scientists tried to resolve the problem of observation in quantum physics was by removing collapse altogether. Instead of asking why one outcome becomes real, they asked a different question. What if every possible outcome becomes real? This idea is known as the many worlds interpretation of quantum mechanics. According to this view, the wave function never collapses. It continues to evolve, branching into multiple outcomes whenever a quantum event has more than one possible result. Each outcome exists in its own branch of reality, forming a vast collection of parallel universes. In this framework, when a quantum measurement occurs, the universe does not choose a single result. Instead, it splits. In one branch, one outcome happens. In another branch, a different outcome happens. Both are equally real, but they no longer interact. From the perspective of an observer inside one branch, it appears as though only one outcome occurred. This interpretation preserves the mathematical structure of quantum theory without adding new rules for collapse. The equations remain smooth and deterministic. All uncertainty arises from the observer's limited perspective within a single branch. Probability reflects not randomness, but ignorance of which branch one finds oneself in. The idea of branching universes can feel overwhelming. It suggests that every quantum interaction, no matter how small, creates a divergence. Over time, these branches multiply into an unimaginably large number of parallel realities. Each contains its own version of events, shaped by slightly different outcomes. Despite how strange this sounds, the many worlds interpretation is taken seriously by many physicists. It does not contradict experimental results, and in some ways it offers a cleaner mathematical picture than interpretations that rely on collapse. However, it raises deep philosophical questions about identity, existence, and what it means to say that something is real. If all possible outcomes exist somewhere, then reality is far larger than the single history we experience. Our sense of a unique, unfolding timeline becomes a local experience within a much broader structure. As these ideas sink in, a new question naturally arises. If reality can branch at the smallest scales, could something similar happen at the largest scales of the universe? Could entire universes form and evolve independently of one another? In the next part, we'll move from quantum branches to cosmic scales and explore how modern cosmology suggests that reality itself may contain many universes beyond our own. While the many worlds interpretation suggests that reality may branch at the quantum level, modern cosmology introduces a different kind of multiplicity at the largest possible scales. Instead of branching timelines, it considers the possibility that entire universes may exist beyond our own, each with its own physical properties and history. This idea emerges from theories about the early universe, particularly cosmic inflation. Inflation proposes that shortly after the universe began, space expanded extremely rapidly. In some models, this expansion never fully stops. Instead, it continues in different regions, causing separate bubble universes to form within a much larger cosmic landscape. Each bubble universe could have its own version of physical laws, the strengths of fundamental forces, the masses of particles, and even the number of dimensions may differ from one universe to another. Our universe would then be just one region in a much larger structure, shaped by specific conditions that allow stars, galaxies, and life to exist. This perspective offers a possible explanation for why the laws of physics in our universe seem finely tuned. Certain constants appear to fall within very narrow ranges that make complex structures possible. If many universes exist with different parameters, then it is not surprising that at least one of them supports observers capable of noticing this fact. We exist in the universe that allows us to exist. Unlike branching quantum worlds, these cosmic universes would be separated by vast distances or regions of space that we may never access. There may be no way to travel between them or even to observe them directly. Their existence would be inferred through theory rather than direct evidence. This challenges our intuitive sense of reality once again. Reality may not be limited to what we can see or measure, but may include structures forever beyond observation. The universe we experience could be a small part of a much greater whole. As these ideas settle, another question begins to form. If multiple universes exist, each governed by different rules, what does that mean for our understanding of identity and existence? And where does consciousness fit into such a vast picture? In the next part, we'll turn our attention inward again and explore how consciousness relates to reality and whether reality can exist without an observer at all. As discussions of reality expand across quantum physics and cosmology, attention inevitably returns to a central mystery: consciousness. No matter how detailed our physical theories become, they all rely on something observing, measuring, or experiencing the universe. This raises a fundamental question. Can reality exist independently of consciousness, or is consciousness an essential part of how reality appears? From a scientific perspective, consciousness is closely tied to the brain. Neural activity gives rise to awareness, perception, memory, and a sense of self. Damage or changes to specific brain regions can alter consciousness in predictable ways. This suggests that consciousness emerges from physical processes rather than existing separately from them. However, the relationship between consciousness and reality remains unclear. While physics describes the structure and behavior of the external world, it does not explain why subjective experience exists at all. Equations can predict outcomes, but they do not account for what it feels like to observe those outcomes. This gap between physical description and lived experience is often called the hard problem of consciousness. Some theories propose that consciousness plays a fundamental role in shaping reality. According to these views, awareness is not just a byproduct of matter, but an essential feature of the universe. Others argue the opposite. They suggest that consciousness is simply a complex pattern arising from simpler physical processes, with no special influence over reality itself. Neuroscience tends to support the idea that consciousness is constructed. The sense of a continuous self emerges from many distributed processes in the brain. There is no single location where consciousness resides. Instead, it appears when different systems work together in a coordinated way. When this coordination breaks down, the experience of self can fragment or fade. This perspective implies that consciousness is deeply dependent on physical reality, but it does not fully answer whether reality depends on consciousness in return. In everyday life, the world seems to exist regardless of our awareness. Mountains, oceans, and stars continue to exist whether or not anyone is observing them. Yet at the quantum level, the role of observation complicates this assumption. These tensions have led some scientists and philosophers to suggest that consciousness and reality may be more intertwined than we currently understand. Reality may not be something that simply exists out there, nor something created entirely by the mind, but a process that emerges through interaction. As we move forward, this brings us to another possibility. What if reality itself is structured like information, and consciousness is part of how that information is processed? In the next part, we'll explore ideas that treat reality as information, including the possibility that the universe behaves like a vast computation. As science continues to search for a deeper description of reality, some theories shift the focus away from matter and energy and toward information. In these views, the most fundamental ingredient of the universe is not particles or fields, but information itself. Physical reality becomes something that emerges from how information is stored, processed, and transformed. In physics, this idea appears in subtle ways. Black hole research suggests that information cannot be destroyed, even when matter falls beyond an event horizon. The laws of thermodynamics link physical entropy to information. Quantum mechanics encodes the state of a system as information, contained in a wave function. These clues point toward a universe where information plays a foundational role. From this perspective, space and time may not be fundamental either. They could be frameworks that emerge from deeper informational relationships. Some theories propose that space-time itself arises from patterns of quantum entanglement. If this is true, then reality is not a stage where events happen, but a network of informational connections that give rise to the appearance of space, matter, and causality. This way of thinking leads naturally to the idea of the universe as a kind of computation. Physical laws can be seen as rules that govern how information evolves. Particles become carriers of information. Interactions become transformations. The universe, in this sense, is constantly computing its own next state. This does not mean that the universe is literally a computer in the everyday sense. There is no central processor, or external programmer implied by the physics itself. Instead, computation becomes a metaphor for how orderly patterns emerge from simple rules applied over vast scales. Consciousness enters this picture as a process that both arises from and interacts with information. The brain processes information to create perception, memory, and meaning. If reality itself is informational, then consciousness may be one of the ways the universe becomes aware of its own structure, at least locally. These ideas remain speculative, but they are taken seriously in modern theoretical physics and philosophy. They offer a way to unify matter, energy, space, and mind under a single conceptual framework. Reality becomes less about objects and more about relationships, patterns, and flow. As we reflect on this, a new question emerges. If reality can be described as information, could it also be generated or simulated by physical systems capable of processing that information? In the next part, we'll explore the simulation hypothesis and examine whether reality itself could be an artificial construct and what that would mean for our understanding of existence. If reality can be described in terms of information and computation, it naturally leads to a provocative idea known as the simulation hypothesis. This hypothesis suggests that what we experience as reality could be the result of a computational process, similar in principle to a simulation, though far more complex than anything we can currently create. The argument does not begin with science fiction. It starts with simple assumptions about technology and probability. If intelligent civilizations tend to develop advanced computing, and if simulations of physical worlds are possible, then over time, there may be far more simulated realities than original physical ones. From a statistical point of view, this raises the possibility that any given conscious observer is more likely to exist inside a simulation than in a base physical reality. From within such a reality, the laws of physics would still appear consistent and meaningful. The particles, forces, and constants we measure would simply be the internal rules of the system. There would be no obvious way to tell whether these laws are fundamental or implemented by a deeper layer of reality. To an observer inside the system, the experience would feel completely real. Some researchers have speculated about indirect signs of a simulated universe. These ideas include limits to measurable resolution, discrete units of space and time, or mathematical patterns that resemble computational constraints. However, none of these observations provide clear evidence. At present, the simulation hypothesis remains a philosophical possibility rather than a testable scientific theory. Importantly, even if reality were simulated, it would not diminish the meaning of experience. Pain, joy, curiosity, and awareness would still be real to the beings experiencing them. The source of the rules would not change the fact that those rules shape a lived world. From a scientific standpoint, the simulation hypothesis challenges us to think carefully about what we mean by reality. Is something real because of how it was created, or because it is experienced? If a world follows consistent laws and produces conscious observers, does it matter whether it is fundamental or derived? As these questions settle, attention turns back to the individual. If reality may take many forms, branching worlds, multiple universes, informational structures, or even simulations, what does that mean for personal identity and the sense of self? In the next part, we'll explore how these ideas affect our understanding of identity and whether the concept of you remains stable across different possible realities. As ideas about reality expand to include multiple universes, simulations, and informational structures, a deeply personal question comes into focus. What does all of this mean for identity? If reality can branch, duplicate, or be instantiated in different forms, what defines who you are? In everyday life, identity feels continuous. You experience yourself as the same person from moment to moment, connected by memory, personality, and bodily presence. But science suggests that this sense of continuity is not as solid as it feels. Neuroscience shows that the brain constantly updates the self model. Memories change over time. Personality adapts to experience. Even the feeling of being a single, unified self is the result of coordinated neural activity rather than a fixed core. If parallel universes exist, or if reality branches at the quantum level, there may be versions of you that share the same past, but diverge after certain moments. From the inside, each version would feel equally real. Each would carry its own memories, emotions, and sense of identity. There would be no clear way to say which one is the original. Identity would become local rather than absolute. This idea challenges the notion that the self is something permanent. Instead, identity may be better understood as a process, a pattern that unfolds over time under specific conditions. As long as the pattern continues, the sense of self persists. When the conditions change, the pattern evolves. Even without parallel universes, this process-based view applies. Every night during sleep, consciousness fades and returns. Every few years, most of the atoms in your body are replaced. Yet the sense of being you remains. Identity survives not because it is static, but because it is continuously reconstructed. From this perspective, reality does not need to provide a single fixed version of the self. Meaning arises from experience itself. What matters is not whether another version of you exists somewhere, but that this version is aware, curious, and capable of reflection. As we approach the end of this journey, these ideas begin to converge. Reality, consciousness, time and identity appear less like separate topics and more like different aspects of a single process unfolding across scales. In the final part, we'll bring these threads together and reflect on what it means to live inside a universe that may be far stranger and more interconnected than it first appears. As we come to the end of this journey, it becomes clear that reality is not a single, simple thing. It is not just the world of solid objects we move through each day, nor only the equations that describe particles and forces. Reality appears to be a layered process, shaped by physical laws, information, perception, and consciousness, all interacting across different scales. Physics shows us a universe where certainty fades into probability, where time bends, space fluctuates, and observation matters. Neuroscience shows us a brain that does not merely receive reality, but actively constructs it moment by moment. Together, these perspectives suggest that reality is not something passively experienced, but something continuously formed through interaction. This does not mean that nothing is real or that the world is an illusion. Rather, it means that reality is deeper and more subtle than our everyday intuition suggests. What feels solid is supported by invisible processes. What feels immediate is shaped by prediction and memory. What feels permanent is constantly changing beneath the surface. In a universe that may contain multiple realities, branching possibilities, or informational structures, meaning does not disappear. It becomes more personal. Meaning arises from awareness, from curiosity, from the simple fact of being conscious within a particular moment of reality. Your experience matters because it is experienced, regardless of how many other possibilities may exist elsewhere. As you rest now, you don't need to resolve these questions. There are no final answers here, only deeper ways of seeing. Science continues to explore the structure of reality, and each discovery reveals both clarity and mystery. The more we understand, the more we realize how much remains unknown. If your mind is still awake, you can let these ideas drift gently, without effort. And if sleep is approaching, you can allow it to come naturally. Reality will continue unfolding whether you are watching it or not. Thank you for spending this quiet time here. Wherever you are in the universe, and however reality truly works, this moment of rest is real enough. Now let your thoughts slow, your breathing soften, and your awareness gently fade. The journey can continue another night.